Okay, let's go ahead and get started. I'm delighted this afternoon to welcome Andrew McCallum from UMass Amherst. Andrew is one of those rare New Englanders who know that Raleigh-Durham is not a city unto itself, having grown up in Raleigh and then done some high school at North Carolina School of Science and Math in Durham. He's the director of the Information Extraction and Synthesis Laboratory at UMass Amherst. He's well known for his significant contributions in the areas of text processing, machine learning, information extraction, data mining, pattern recognition, both in industry and in academia. In addition, he's quite active in the community, including, among other things, being program co-chair of this year's ICML International Conference on Machine Learning. So Andrew, welcome back to the Triangle. Delighted to have you here with us today.
All right, thank you so much, Alex. It's great to be back in North Carolina. And I was visiting my parents just this weekend, and they were showing me their flower garden and how the flowers are all still blooming, and I can tell you that that's not happening in New England right now. And it's great to be at Duke. This is really my first time as an academic visiting Duke. So in my research, I care about building models that mine actionable knowledge from unstructured text. And I feel like there are many people who are in a situation somewhat like this. There's some sense in which she could make much better decisions if she had access to the vast amount of knowledge that's sitting in that unstructured set of documents and the text in it. And if only she had the right tools that could help her understand that massive amount of data, find patterns in that data, help provide decision support, that she could do her job better. So let me give you some other more specific examples of what I mean by this from my own past. And in fact, I'll start with one of the industrial examples that Alex was mentioning. Before I was an academic, I helped found a startup company that extracted information about job openings directly off of company websites. We built a system that would start at the homepage of a company like this, automatically navigate through it to find the section where the company lists their job openings, and then used various sophisticated statistical models to automatically segment job openings from each other, extract the job title, description, location in the country, contact information for how to apply, etc., and build database records that look something like this. We then made it available through a website to the public. We scared the pants off of Monster.com because we had twice as many job openings in our database as they did at the time. And we of course made available very nicely structured, rich set of queries with nicely displayed results, and many people found this very useful. What I found most interesting was that now that we had this database, not only could we offer search over this database, but we could mine this data for patterns. And we did this once a month. We ran various kinds of data mining algorithms, discovered patterns, high-tech jobs on the rise in the South and falling elsewhere, et cetera, and published this report. And we heard anecdotally that there were several state and local governments that were using this report to help set governmental policy because nowhere else could they get information that was this complete or up to date. One other example before I move on. The Chinese Academy of Sciences has several 100,000 documents that are literally several millennia old. They're Qing Dynasty archives, memos, newspaper articles, diaries, and they contain a wealth of information about many things, including information about the weather. Right, these are people saying, my cherry tree bloomed early this year, or my fields have flooded and my crops are bad. And these are scientists who are studying long-term weather trends. And this data about what the weather was like so many thousands of years ago is so valuable to them that they're having humans go through these documents by hand to extract information about weather events. But they're having a little bit of trouble with this 200,000. And so we've been thinking about ways to help them automatically extract this structured information from unstructured text to do the kind of mining that they need to do. All right, so let's step back and talk about information extraction as a whole to situate us. It involves building a database, a structured database from unstructured text. And as a family of techniques, this involves segmentation to find the boundaries of the field values that you're going to extract. Classification, to say that this is a company, this is a job title, this is a person's name. Association, to say this person had this job title at this company. And then also clustering or deduplication, to collapse duplicate information so you don't have a lot of messy repeats in your database. And you don't necessarily have to perform all these things exactly in this order or as separate steps. In fact, a big part of what I'll argue is about how you want to consider these steps all together. So here's the larger picture. We start with some document collection of unstructured documents here. We perform some steps of extraction. This gives us a database. The database is not an end in itself. What we really care about in the end is things like prediction, outlier detection, decision support, and going from, and data mining is how we get from the database to those things. All right, so this is a beautiful picture. There's just one problem, and that is that, well, there's not just one, there are many problems, but the problem that's on my mind right now is that extraction is not perfectly accurate. It makes mistakes. And it never will be perfectly accurate. You will always make incorrect extractions, extract too much of one thing, be missing boundaries, and things like that. So our database has errors in it, and there are many data mining algorithms that, when run on those errors, will be brittle, will produce errors and produce garbage out the other end. And this kind of problem of cascading errors appears in many places, not just in extraction and data mining. Consider even just a classic natural language processing pipeline in which we begin with words at the bottom here, do some kind of low-level natural language processing like part of speech tagging, noun phrase chunking, parsing, followed by finding entities like people and locations, semantic role labeling to say something about verbs and the various arguments to verbs, anaphora resolution, pragmatics, etc. So, these are all various subproblems of NLP that the community has been working on for some time, and we've been attacking them as individual problems. And at long last, after many years of work, we have fairly accurate solutions to each one of these problems. Part of speech tag accuracy is well up in the 90s. Parsing is somewhere in the low 90s, etc. We might be feeling like we're done and we've done a good job, but the problem is that 90% accuracy may sound high, but you put these together in a pipeline and those errors cascade very quickly, right? You don't have to raise 0.9 to a very large power before it's less than 1/2. The problem is that once you've made some error at some lower level, it's very hard to recover from it later. So if you think about how do humans solve this problem, well, we have, we don't just think about part of speech tagging, lock in on one set of tags before we move on to the next step. We're thinking at the same time about pragmatics and semantics and this high-level reasoning to help inform us about what's the proper parse for this sentence. And so, really what we should be thinking about is a unified joint inference over all of these things at once, so that we have inference flowing both bottom-up and top-down. We have high-level semantic constraints informing how we make these low-level decisions. And this same kind of reasoning applies to extraction and data mining. Rather than passing a single hypothesis forward from extraction into the database, really we should be extracting multiple hypotheses with uncertainty information, passing that into data mining, which has been reconfigured in some way to consume this probabilistic information, perform data mining here. Some initial patterns will emerge, and note that these can be fed back into extraction, which is sort of desperate for some top-down semantic level knowledge to help it do a better job, and we can close this loop. And as we all know, closed loop systems often work better than open loop systems. So even more dramatically, I like to think about this extraction and data mining as really a single unified model in which the boundaries between them begin to disappear, and we have some sort of probabilistic model in the middle substituting for the database. And this might sound somewhat crazy, but it's not really that bad. And one thing that makes me believe this is noting that research in each of these previously separated communities has been recently finding great success with the same underlying statistical kind of model. these things known as discriminatively trained undirected graphical models. In the natural language processing and extraction community, they're often known as conditional random fields. In the data mining community, there's been a lot of work on these conditional probabilistic relational models, and they've each had great success. But really underneath, it's the same kind of statistical model. And so we could think, well, we've got the same kind of model on both sides. We can just stick them together into one big model. They'll know how to talk to each other and how to work together, and it will all work. So now, of course, inference in each side of this was pretty complicated before we got started, and we're only going to make life more complicated when we put them together to make this truly massive model. But of course, these kinds of challenges are exactly what make us researchers wake up in the morning with a smile on our faces, ready to launch into a new day's challenge. So, what are some of the scientific questions that arise in this kind of view of the world? Well, what model structures will capture salient dependencies? We can't afford to put dependencies everywhere, but we want to put them in the right places to capture the dependencies that are important. Will joint inference actually improve accuracy? It's a nice storyline, but in practice, when we run this on real data, will it actually really help? We're going to build some very large models, and how can we do inference in these large graphical models and make it efficient? And furthermore, how can we do parameter estimation efficiently in these models, which are built from multiple large components? And then there's also this question of how to do structure discovery. So today, I'm really going to focus on inference and parameter estimation in these large models. And as you'll see, this gives rise to a number of really juicy mathematical problems that have some interesting solutions. And along the way, I'll describe some empirical results that give us some hope for for further success in the future. All right. I'm going to skip this slide. So here's the plan. I've motivated joint inference and given you some examples of extraction and data mining. I'm going to briefly introduce conditional random fields as the underlying technology that we're going to use in both of these cases. And then I'm going to give you a tour through various examples of joint inference in this problem. And most of these are really, they're examples of joint inference, but they don't yet reach very far into the data mining side of things. I could give you some pointers to that work later if you like. And then I'll conclude with a demo of a system that we've built that uses some of these techniques. All right, okay, so let's talk about conditional random fields, beginning with a model that I hope you're all familiar with already, and this is the Hidden Markov Model. So we're going to talk about actually the first two steps of extraction that consist of segmentation and classification. And we take as input the sequence of words, and so we're going to turn to a really classic sequence modeling method to address this. So let's, even though I imagine you're familiar with this, let's get on the same page in terms of notation and a few things. So what is a hidden Markov model? It's a finite state machine with probabilities on both the transitions and on the emissions. To operate this model, you begin in some state that you choose according to some distribution, and then you roll a die to decide which outgoing transition to take. Let's say that you take this one. You arrive in some state. You roll another die that's sitting inside of that state to decide what symbol you should emit, after having arrived there, and then roll another die to make another transition, and so on. So as you turn the generative crank on this model, what do you produce? You produce a sequence of states and the sequence of observations that you emitted along the way. All right. So here on this side is another circles and arrows drawing. Not at all to be confused with the finite state machine on this side. They're representing, the circles and the arrows have a different meaning. So here, each circle corresponds to a graphical model, a random variable that take on various values from this model. In a way, you can see these sets of circles is exactly corresponding to what gets generated when you turn the generative crank on this model. These upper circles are random variables that take on values being one of the states of the finite state machine. And the circles in the bottom correspond to the observations that were generated as you visited those states. So the values these take on are the observation symbols. And lastly, just to get some notation here, so this is an equation that describes what the hidden Markov model generates. It produces a probability distribution over sequences of states, sequences of observations, and how does this do it? By a product through time of each one of the transition, state-to-state transition taken according to this probability, and the probability of producing each observation given the state that you arrived at. Okay, all right. So how do you apply these models to hidden Markov to information extraction? You're given some sequence of observations, such as this one here, where each word is an observation. You're given a hidden Markov model in which the parameters have already been learned or set. And furthermore, each one of the states is associated with some field in a database. And then you search for, given this sequence of observations, the state sequence that was most likely to have been co-generated by the HMM along with this word sequence, and which can be done efficiently by dynamic programming in an algorithm called the Viterbi algorithm. And any words that Viterbi says were generated when you were in, say, one of the red states, you extract as being a person name. All right. So I should pause to say I would very much welcome any interruptions or questions, so please, anytime, don't hesitate. In fact, I'll be disappointed if you don't ask questions during the talk. Okay, all right. So, so hidden Markov models have, were sort of the state of the art in information extraction sometime around the late 90s, early 2000s, and they did pretty well. But we did have a number of regrets with these models. And the first thing, actually, is to note that the view that the hidden Markov model has of its observation sequence is the words themselves and this multinomial distribution over emissions that sits in each state. So you essentially see the word itself and really nothing else. But really, we'd like to have a richer representation of the input text. We'd really like to be able to capture many arbitrary overlapping features of the words. So in other words, well, for example, consider the case in which at test time I'm doing extraction and I come across the word Wisniewski. It's not a word that I saw at training time, and so the hidden Markov model, when trying to decide what to do with this word, to decide, is it a person's name, a location, an organization, or something else, just knows that it's the unknown word token, and it knows just a little bit about its context and some of the transition probabilities. But if instead of that situation, I knew that not just the identity of the word, but the fact that it ends in the character string SKI, that it's capitalized, that it's part of a noun phrase, that it's not in a list of city names, these can all be small pieces of evidence that I can combine to help me decide correctly that it's a person's last name. All right, so I want to include these extra features. How do I do it? Let's see here. So there's a major problem with including all of these extra features that I want, and that is that these features are not at all independent of each other. They're highly dependent. They're highly correlated. I'm asking questions at multiple levels of granularity about characters, words, and phrases. I'm asking about multiple dependent modalities like the words or the formatting or the layout I might want to ask about. Or I'm also asking questions about the past and the future, which are certainly highly correlated in this sequence. So when faced with these dependencies, I have two basic choices. I could choose to model those dependencies, capture them with additional arcs in my graphical model that represent the fact that, well, when I'm generating this feature, I should examine this one and have extra parameterization that captures that dependency, or this other alternative. But modeling these dependencies is really not an option because I'm just, it vastly increases the number of parameters that I need in my model, and I'm already just starved for training data as it is. There's no way I'm going to be able to accurately fit the parameters of this model with all these extra dependencies. So my other option is to ignore the dependencies, treat this more like a naive Bayes classifier, just generate each one of these features independently, and that might work pretty well in a naive Bayes classifier, which often have surprisingly good accuracy. But if you've ever used a naive Bayes classifier yourself or played around with them, you'll note that the output probabilities that they give usually give probability very close to 1 to the winner and very close to 0 to the rest, because making these independence assumptions causes the model to be overconfident in its output. And in a classifier, that may not be such a big deal. When you're trying to operate over some sequence in which you're combining evidence up and down the sequence, it's a disaster, right? I mean, one of the ways I think about a hidden Markov model, the magic of a hidden Markov model is that you can change your mind about where you thought you were based on evidence that you see in the future. But if you are so confident about where you thought you were, you're just not going to be able to change your mind about it, and you lose a lot of the power of the hidden Markov model. Okay, so neither one of these things are really going to work. So this makes us interested then in conditional probability models. We'd really like to we prefer a model that's trained to maximize a conditional probability rather than a joint probability, modeling the probability of the state sequence given the observations rather than the joint probability that would generate both of them. So this means that we can examine all these fancy features that we want, but we're not responsible for generating them. It means that we don't have to then explicitly model their dependencies. And there's some sense in which we're not wasting modeling effort trying to generate what we're given at test time anyway. All right, so here's the motivation, and here's and now next is your one-slide introduction to conditional random fields. Good luck. Okay, here we go. So it's not as complicated as it might look. Up at the top, we have our old friend, the hidden Markov model. This formula is exactly copied from the previous slide, and this graphical model is also. So here we have the hidden Markov model's joint probability over both the state sequence and the observation sequence. And what I want is a conditional probability of the state sequence given the observation sequence. Okay, so how do I get there? Well, we all know just from basic probability, if I have, probability of A and B, but I want probability of A given B, well, how do you get there? Well, you divide by the thing you want to condition on. So that's what I've done here. I just copied the equation from above, and I'm adding this one term that's dividing by the thing that I want to condition on. And so this actually is a valid formula for this conditional probability. But there's still a problem here, and that is that deep inside the calculation of the conditional probability is still a generative probability of the observations, of these observational features, and that's exactly what I wanted to get rid of. Okay, so there's an extra step in here, and that is to note that just because I want a normalized probability distribution out of the model at the end over entire sequences, that doesn't mean that the individual constituents that I multiply together to get that probability have to be normalized probability distributions themselves. So I'm going to relax the parameterization somewhat to say that, well, my parameters are not going to be normalized distributions. They're just going to be, I'm going to change them to these phi's that take the same arguments. And you can think of these phi's as just compatibility functions that return numbers between 0 and positive infinity. Okay? Where 0 means when I look at these these arguments, I think it's just completely impossible that I would see them together. And infinity means it's absolutely certain that I would see them together. And yeah, you can think about this as, again, an unnormalized compatibility function. And so when I take this product, I'm going to get some sort of score for how much I like the fact that I've just seen this observation sequence and state sequence together. It's not going to be a normalized probability distribution. So I need some sort of normalizing factor here to make it into a probability distribution. Here, it just turns out that that normalizing factor is exactly the probability of the observation sequence. Here, that's no longer really the case. I need, whatever extra terms are needed to make it normalized. And what this normalizing term is simply is exactly what you would need to normalize any kind of distribution. It's the sum of the values of all the different possibilities, and that's what you divide by to make something, to make the distribution sum to 1. Okay, and I don't have time to get into a lot of the details of exactly why, but this extra degree of freedom that allows for these constituents to not be normalized probability distributions is exactly what allows me to tune the parameters of my model so that these features that may be overlapping with each other, I can essentially make up for those overlaps by leveraging this extra degree of freedom in tuning these parameters, and any variables on which I'm conditioning that have these dependencies will essentially be taken care of for me by the model itself. Now, it's my choice how I want to parameterize these fees. One common choice, just for its mathematical convenience, is to use a log linear model, which is essentially an exponentiated sum of some weighted features. These features are exactly the kinds of questions that I was asking earlier about words. Are they capitalized? Are they a noun phrase? So you can think about these as binary indicator functions that are either just 0 or 1. That either choose to include or not include some learned parameter weights lambda in this sum, which then gets exponentiated. Okay, questions? All doing okay so far? Okay. So, I mean, just some of the mathematical details may not matter, especially for the rest of the talk. You can think about this model in a way as a kind of discriminatively trained hidden Markov model. So it is also a finite state machine. It happens to be represented by, instead of a directed graphical model with arrows, an undirected model that reflects the fact that I don't have normalized probability distributions for parameters. And this kind of model has been applied not only in natural language processing, but in bioinformatics and computer vision, and many, many different areas. And in many competitions, these kinds of models are the ones that are winning the competitions. This finite state shape model is just one particular choice for a structure, and in the rest of the talk, you'll see many examples of some other structures. All right, so to get a sense of how this works in some real data, let's look at just quickly a couple of examples. Let's say that we are trying to extract tables from the text of governmental reports. So these are ASCII documents that come from the government that report on various things, and they consist of some free-flowing paragraphs, and then every once in a while there'll be a table sort of drawn in ASCII art like this, and it's our job to find the table and separate out its constituents, its title, its header rows, its data rows, its footnotes, etc. So we're labeling lines here effectively. And the way we can set this up as a conditional random field is to say, well, my emissions will be entire, or sorry, my the observed variables at each time step will be an entire line, and I'm trying to label each line with one of about 12 different labels that look something like this. And for features, I have many different features of the contents, the context, of the format, of the layout, of all these things, as well as conjunctions of all of these features. And let's see how it does. So the hidden Markov model at 65% basically does abysmally. And here it's just really bitten by the fact that these features are highly correlated with each other. The decisions become way overconfident, and it's not able to leverage the magic of a hidden Markov model, and does quite badly. This next line, a stateless maximum entropy classifier, this is it's a discriminatively trained model. It's able to handle the overlapping features, but it's classifying each line independently of the others. There's no Markov model here. It's not taking advantage of the context of the labels. And so this does a bit better. And the conditional random field does best of all. And in some ways, you can think about the conditional random field as the combination of the discriminative training of the maxent model and the Markov property of the hidden Markov model.
Did you?
Yeah.
This is Christopher in Raleigh, or in Durham. Did you say that the HMM is this an HMM where the features are considered independent?
Yes, that's right. That's right. Yeah, thank you for asking. Yeah. Okay, one other example that we'll revisit again later. Let's say we want to do information extraction for research papers. We have the PDF, we turn it into text, we want to extract the titles, the authors, the institutions, etc. A hidden Markov model, which we did in some earlier work when I was at Carnegie Mellon, gets a 75% accuracy. Another discriminatively trained method that whose Markov property is maybe not fully leveraged does better, and the conditional random field really does does quite a bit better. All right. Okay. So, and other broad questions about conditional random fields before we continue? Another way you can think about it is that it's like a logistic regression classifier in which the output is not a single binary variable, but a very large structured object with dependencies among the variables. Okay. No? Okay. All right. So now let's talk about some examples of increasingly joint inference as we look at pieces of text. There'll be some quick ones in the beginning and then some longer ones. So let's say that we're trying to do named entity tagging. We're given English words as input, and we want to label those words as to whether they're people, organizations, locations, etc. And it turns out that for this task, it's useful to have as intermediaries accurate part-of-speech tagging and noun phrase boundaries along the way. But of course, our input Wall Street Journal article doesn't provide part-of-speech tags and noun phrase boundaries ahead of time. We actually have to predict those as well. So the traditional solution is that you take your words, you put them through some finite state, maybe a conditional random field part-of-speech tagger. You find the most likely part-of-speech tags, lock those in at their most likely values, and then use those words and the part-of-speech tags to predict the noun phrase boundary tags, lock those in at their most likely values, and then finally predict the named entity tags. But of course, this has exactly that cascading error problem that we were talking about earlier. If you make a mistake in your part-of-speech tag, it's incredibly hard to recover from that later. And there are, in each one of these layers of the cascade, opportunities for more and more mistakes. So in something that we call a factorial conditional random field, we can do joint inference over all of these different layers all at once. The lack of shading in them reflects the fact that I'm not committing to any one answer here. I'm not treating it as observed. I'm going to simultaneously predict part-of-speech tags, noun phrase boundaries, and named entity tags all at once, not committing to any one part of this before I've viewed all of the dependencies together. So I've just constructed a graphical model that has a lot of loops in it, in which many of you might know you can't do exact inference very efficiently. But there are various methods of approximate inference, loopy belief propagation being one of them, and in this particular problem, it happens to work well.
Is there a factor graph representation of that kind of model?
Excuse me?
Is there a factor graph representation of this model, a direct one-to-one mapping between factor graphs and this kind of approach?
Okay, let's see here. So, yeah, factor graphs is a term that I use also, and I assume that we're talking about the same thing. We're talking about undirected graphical models in which I would typically also draw these little black boxes that represent actually exactly the fees that were in the earlier equation. So yes, I mean, I guess this is a factor. I could, if I had only drawn those little black boxes on each one of those edges, then yes, this would be the factor graph that we're talking about. Does that answer your question? Okay. Okay, so that's one example. Here's a second example of a kind of joint inference of a different sort. Let's say that, again, I'm doing named entity extraction, and I'm trying to find names of people, among other things. Here, when I look at this word here, green, there is a lot of local evidence that that is a person's last name. Right? It's preceded by the word Joe, clearly a person's first name, which is in turn preceded by an honorific. It's followed by the word said, and these are all strong pieces of evidence that help us decide this is a person's name. Here's another instance of the word green where there's almost no local evidence that this is a person's name. Right? This could be paint that I'm talking about here. Right? But these two instances of the word green appear in the same document. And so there's some sense in which I should think, well, the label that I put in one instance of the word green within the same document should not be independent of the label that I put in the other. Maybe they should be a bit more correlated. I'm not going to force them to be the same, but I should somehow capture the fact that there's some dependency between them. And so when we add these long arcing edges to the linear chain CRF in a model we call the skip chain CRF, we're capturing this extra dependency, and indeed we get an improvement in accuracy. This model, although it may look simpler, actually inference is harder in this model. Loopy belief propagation doesn't tend to converge. But in some work by Martin Wainwright and others on tree reparameterized belief propagation, it tends to work well. Okay, another example. Co-reference resolution. And on this one, we're going to take our time and go into a bit more depth. So let's first talk about what the problem is. Co-reference resolution actually has many names itself. It's fundamentally the same problem as record linkage, database record deduplication, citation matching, object correspondence, and the rest. In fact, it's kind of a little bit of an inside joke that the name of the research area that is concerned with the same object having multiple names itself has so many names. And so here in this one sort of classic natural language processing instantiation, the problem is the following. We take as input say, some news article in which all of the named entity mentions have already been tagged. So I've found the boundaries and the classifications of these phrases that are referring to people. And it's my job as output to decide how many different people are being discussed in this article and which mentions are referring to which person. So in essence, it's the kind of clustering problem in which I don't know how many clusters there should be ahead of time. And it's just a deep and a challenging, difficult problem. Okay, what does the traditional solution look like? I consider every pair of mentions, and I ask yes, no, are these referring to the same person or not? And I do it by learning and then leveraging some pairwise affinity metric. I look at many features of the pair, both their contents and context and how far apart they are from each other, various things like that. I look at the features that are on for this particular pair. Each one has a weight. I sum up the weights. If the weight is above some threshold, then I say, yes, they're coreferent. So I essentially am building a graph of yes edges and then taking connected components in that graph, and each connected component I'll declare to be an entity. And this has been the traditional solution for quite a few years. So I want to go through a bunch of examples and do it in terms of these figures, so let me set up the context here. So here we have 5 mentions of people. And essentially the problem is to decide where the entities are. It's a kind of clustering problem to say, well, do these 3 mentions correspond to one person and these to another? Or should it be clustered this way instead? Or are there not even 2 entities, but actually 3 entities instead? And the traditional, I'll draw the traditional solution somewhat like this. Actually, here I did draw the factors for the factor graph. I'm looking at each edge, and I, between 2 mentions, and I'm trying to decide yes, no, are they referring to the same person with this affinity metric between them represented by the black box. And I decide for each pair, do I consider them coreferent, in which case I've drawn a little C inside the box, or not coreferent, in which case I put an N. And what does the traditional solution do? Well, it looks at these 2 and says, well, I think Mr. Hill and Dana Hill are coreferent. I think Dana Hill and Dana are coreferent. I think Amy Hall and she are coreferent. And then there was maybe something about the local grammar that made me think that Dana and she were also coreferent. Okay, so now my next step is I go ahead and take connected components to decide on the clusters, and I see, well, this is connected to this, is connected to this, is connected to this. They're all connected. So it's all one big connected component. My solution is this. Well, there's something clearly very wrong with the situation. I've just said that she is coreferent with Mr. Hill, and so clearly that can't be true. Something's gone horribly wrong. What was the problem? I mean, I made these pairwise merging decisions in a way independently of each other when I really should have made them jointly all together. So we can solve them jointly by essentially turning this entire model into a large conditional random field. It's not at all shaped like a linear chain or on a sequence. It's a conditional random field that looks at a fully connected graph of mentions in which I'm going to jointly predict all of these n's and c's all at the same time. And I can write down an equation for this. The y, this y variable is corresponding to all these the n's and c's that I'm trying to predict. X is the set of all the mentions. How do I decide how much I like some particular choice of coreference decisions? Well, there's one term that looks at every possible pair of mentions and many features of the pair. This is essentially the affinity metric that I had before. And then there's some other constraints that I'm going to add to the model that essentially say you're not allowed to violate transitivity in these decisions. So right now, I mean, look at the current coreference decisions here. I'm saying that she and Dana are coreferent, and Dana and Mr. Hill are coreferent. But on this edge here, there's an N. I'm saying that these 2 are not coreferent. So this is like saying A is equal to B is equal to C, but A is not equal to C. And I'm just, this extra term on my model is going to say you're not allowed to do that. And it's going to be governed by this parameter lambda prime, which is not going to be learned. It's going to be fixed at negative infinity, just hammering the solution into that hypothesis into the ground, saying it's not allowed to happen. Okay, so let's see how this works with some particular examples. These numbers are reflecting these pairwise affinity metrics. And whenever I flip an n to a c or vice versa, the sign on these affinity metrics change. Here is one coreference decision. I can look at the contribution to the score that comes from all of the pairwise affinities and see that it looks good. But then I see, oh, I'm violating a transitivity assumption, so that gets a negative infinity. The total score is negative infinity, and I really don't like the solution. The problem is right down here, right? In essence, locally, I'm saying the model is saying I'd like these to be coreferent, but globally that just produces inconsistencies. So I'm going to change that c to an n. Locally, the score, which used to be a positive contributor to the overall affinity metric, now just became negative. So I lost a little bit of score here, but I just, I gained a lot in my overall transitivity constraints. And now I can look at the score of this. Well, the negative infinity goes away because I'm no longer violating transitivity. And the clustering corresponds to one that looks like this. And now I can ask about the affinity measure portion of this and see that I get a number that's not quite as high as it was before, but it still looks pretty good. So this is one partitioning, and inference in this model consists of considering many possible partitionings and seeing which one the model prefers. So for example, we might consider a partitioning like this also, having changed some of the n's and c's, and we can evaluate that too. That doesn't violate transitivity, but the pairwise affinity measures, we just really violated some very strong green edges here, and we didn't, we produced like a score of -12. We really didn't like that at all. So we liked the earlier one better. All right. So these examples are designed, hopefully, to make it obvious that this is a particular kind of graphical model in which inference corresponds to graph partitioning. It's a special kind of graph partitioning with both positive and negative edges. In which inference is difficult, but there's been a lot of work in the theory community about considering models like this that we can leverage and do a good job. And in fact, on real newswire data, reasoning in this way really does help substantially. All right, okay. But now I want to tell you, just after having introduced that model, that actually we didn't go far enough. That that even though we're now doing joint inference among all these pairwise decisions, just the fact that we're measuring pairwise affinity, measuring only pairwise affinity is not enough. We need something more than that. And to illustrate this, I'm going to change my example a little bit. I'm going to change these 3 mentions on the left to be the word she. And here we have a particular set of coreference decisions that correspond to a clustering like that. Now you might look at this initially and think, well, this looks pretty good. I'm not violating any gender problems, and all looks fine, until I think a little bit further and I realize, what is this really saying about this news article? It's saying that here on the left is some mention, so there's some person that's mentioned in this article that's never mentioned by name. Right? I'm only ever referring to this person as she. And that just seems pretty unlikely. And so I would like some way to say that I don't like this answer. It just doesn't seem that likely to me. But this model does not have the power to recognize this problem, right? Because it's only looking at pairs of mentions. It sees these 2 she's within the same cluster and says, well, that seems good. It sees these 2, that seems fine too. It sees these 2, that's fine also. Nowhere does the model have the ability to see that, well, all of the mentions in this cluster they're all pronouns. And this is just one example of a case in which we'd like to be able to ask more complicated questions. So not only just are all mentions pronouns, but so I'm not sure whether I'm going to have the time to explain a lot of these in great detail. There are other cases in which entities have multiple attributes, and you really need to measure compatibility among these many attributes all at once, and you can't really notice the full set of compatibilities unless you look at them all together at once. Or there's some sense in which having 2 given names, like a first name and a middle name, is quite common, but having 4 is not common. And you could decide that certain sets of mentions are coreferent pairwise by being a little bit confused about which is the first or the last names, or rearranging these things. But if you make too many rearrangements, you've just created somebody with 3 or 4 different first names. Or there are other kinds of questions that you could ask if you could view the entire set of mentions in a partition all at once. If you just want to measure the size of the cluster, or ask questions like, well, does there exist some pair of last name strings that differ by some threshold? So what we really want is we want to be able to ask there exists, and for all questions about some arbitrarily sized set of mentions, we want first order logic. And so this is the next kind of model that I want to talk about. So instead of building a graphical model, a factor graph that looks like this, essentially I want factors that look something like this. Right? Inside this factor, I'm able simultaneously to look at all of the dimensions of the partition and ask some arbitrary question about all of them at once. And maybe I'll also have some factors that will compare, across mentions as well. And within this factor, ask arbitrary questions in first-order logic to do this. Yes?
Back to what you were saying before, why couldn't this all be addressed using some type of clique hypergraph?
Well, I think that's, if I'm understanding what you're saying, I think that's what this is.
That's what this is. Okay.
Right. Yeah. Yeah. I mean, effectively, right? Here's a partitioning. I'm saying these belong all together, and I'm putting a factor on something. Good. Yeah. And I'm glad you asked that, though. So this is one example of combining logic and probability. These are two branches of AI that have, for too long, been separated and not on speaking terms, perhaps, or not talking to each other as much as they should be. And this represents one effort or one way to get them talking to each other again. I feel like both sides have maybe reached the level of maturity that they're ready to begin talking to each other again. Okay, so of course this kind of partitioning represented by this graph is just one hypothesis about what the correct coreference decision is. And then in order to do inference, in order to search for what I think is the most likely coreference decision, I have to examine not just one, but consider, well, what if maybe this is the right answer? I should score this one also, or maybe it's this one, or maybe it's this one. And to do full inference, I should consider many of these different graphs in order to find the one that scores the best. And the problem is that there are a lot of them. Yes?
Look over all of these. Do you worry about issues like global consistency in terms of marginalization and conditioning?
Well, let's see. So there's consistency of making sure I don't violate transitivity, but you're now talking about making sure there's some margin between the score of the best output and the runner-up?
No. What I'm saying is, in some sense, this should satisfy rules of probability, right? So given any separator, any arbitrary separator, I should be able to take the two different sets, and then if I look at the overlap between them, right, the marginal should be the same. This is classical notions of global consistency in the context of graphical models, a la Lorentz and Right. So is that an extra condition that
I don't think that's. I mean, I think that just by the fact that we're normalizing by the partition function here, that this is falling out. I mean, we could maybe talk about this more offline if you think that it's still an issue. Okay. So this is not just a big space to search. I mean, before we were getting over some of the search problem by doing some approximate inference. We were doing that approximate inference through some sort of message passing algorithms, the variants of loopy belief propagation. But to do loopy belief propagation, you have to allocate memory for all of your factors to have some data structure in which to pass these messages. The problem here is that there are a lot of factors. Right, here we're just looking at 5 mentions and thinking about how many different ways there are to divide 5 objects into subsets. There are a lot. But, in real data, it's not just going to be 5. It's going to be more like 200 or 300 mentions. And so there's just no way that we can allocate enough memory for all of these factors. We can't even, never mind being able to do inference on the graphical model, we can't even instantiate the graphical model in memory. So, this kind of space complexity is not unique to coreference. It's common in probabilistic first-order logic models. So, there's been some work in this kind of approach called Markov logic, that in which you write down some logical clauses, assign weights to them, and in very much the way that we just discussed. And when you do inference in these models, you unroll them, and which is also called grounding out the Markov network. And doing so requires space that's exponential in the clause arity. And so it's a bad situation. Just really, it's hard to make it scale to large amounts of data. So we're faced with this question: how can we perform inference and learning in models that can't even be grounded? I can't even fit the model in memory. So let's talk about that for just a little bit. So the standard ways of solving these weighted first-order logic things initially have been to use these weighted SAT solvers. There's been such success in SAT solving for many tough problems, and it indeed works well. But it requires a complete grounding of the network, actually. So it really, it doesn't scale. There's been some work in a method called lazy SAT that saves memory by only storing a subset of the clauses, those clauses that may become unsatisfied. But it still requires exponential time to do initialization at the beginning. Okay. So this leads us to think about some other methods of inference based on Monte Carlo Markov chain. One simple example of which is Gibbs sampling. So this has saved us some memory in the fact that we're only really instantiating memory to store one configuration at a time. And we consider just changes to this configuration in a more local fashion. And Gibbs sampling is probably the most local of these, right? I just visit one variable at a time, let its value float, conditioned on the variables, the rest of the variables that's in its neighborhood, whose values I'm going to keep locked. Calculate the distribution over that one variable, sample according to that distribution, and then move on in round-robin fashion to the next variable. So this doesn't have the memory problems, but Gibbs sampling often makes it difficult to move between high probability configurations by changing just single variables at a time. There are times when I really need to change multiple variables in concert in order to jump from one kind of solution to another, so it can get stuck in these local minima. So another MCMC method that's an alternative to Gibbs sampling is Metropolis-Hastings, which comes in two parts, a proposal distribution and an acceptance distribution. It can be extended to these so-called partial configurations in which we're not instantiating the whole model at once. It's been successfully used by other people who are combining logic and probability. And in my mind, the key advantage is that we can design arbitrarily smart jump functions, which I'll say a bit about, a little bit further about in a minute. So what's the big picture here? Instead of building the factor graph that would represent all of the configurations on which I'm trying to do inference, I just represent one at a time. And then I design some sort of jump function that looks at my current configuration and proposes some new configuration based on the previous one. And these jump functions, I can design this jump function myself, and I can make it, I can sort of bake in some domain knowledge that I might have into this jump function. If I know that certain variables really are highly correlated and should be changed in concert, I can make sure that my jump function does that. And so the way this works is, I have my old configuration, my jump function proposes a new configuration, I score that new configuration, I decide how much I like it, and I decide whether to accept the jump and continue exploring from there, or to reject the jump, go back to where I came from, and continue in some other different direction.
So when you set up these junction trees or whatever have you and have them parameterized, are you always going to have the same number of parameters in this, or do you have to worry about a reversible jump step if you have a different number?
Yeah, okay, good. So I might want to take some of this offline. The answer is in some cases we have to worry about the reversible jump, but in most cases we can consider the partition function to be over all possible partitionings of the data, right? And so those things just factor out. Now, one thing that makes this feasible is that we're not actually trying to do Bayesian inference over our parameter settings as well. That's where, right, it gets really fancy, and you have to think about how, if you want distributions over your parameters, things get tougher. We're just going to take a point estimate of our parameters, and we're just trying to do inference over the data parts of our model. Okay. Okay. So, at the heart of Metropolis-Hastings is that I make this jump and then I decide whether or not to accept it. And that acceptance probability consists of two parts. It's a ratio of the probabilities of the data variable settings themselves. This is just how much do I like this configuration. And then there's this extra factor here that makes up for the following situation. You're going to bake your domain knowledge into this jump function, but when you do that, it's very likely that this jump function is going to be biased in some way. And that bias can be a real problem. And I can motivate that by painting with my hands the following simple picture. Let's say that you're trying to do inference or optimization in some simple one-dimensional space in which I'm jumping left and jumping right. And you can think about some optimization surface or some likelihood surface sitting on top of this that's bumpy in various ways. If my jump function is set up to be biased to jump left more often than it jumps right, then I will very heavily explore the left region of space over here and hardly explore the right region of space at all. And I'll have lousy inference or lousy optimization as a result. And so I need to make up for this bias, and this is exactly what this second term does. It takes the ratio of the forward and backward jump probabilities to make up for that bias. Okay, so the next problem is that we now have a model and we have some sense of how we're going to do inference. But I'm also interested in learning. I want to learn the parameters of this model so that when it does do inference, it arrives at the correct solutions. So I want to learn the parameters of this scoring function here. And let's talk about how to do that. So this is, I'm really dealing with massive state spaces here, and this is going to be problematic. The classical methods for doing parameter estimation involve just simply writing down the log likelihood of the data, or the conditional likelihood of the data, calculating the gradient of that with respect to each one of your parameters, and doing gradient hill climbing to get there. And this is essentially exactly the way we fit the parameters of a linear chain CRF, and it works great. Calculating these gradients, if you look at the equation for that gradient, inside of there are these expectations of marginal distributions in the model, right? Effectively, what the model naturally gives me is a probability distribution over all of these variables, all of these y's all together. But what I need is these distributions over just single variables in which I've summed out all of the rest of the variables. And doing that summing out or calculating those marginals can be quite expensive, especially in models that are as complicated as this. So I'm essentially in big trouble. Getting these marginals is incredibly difficult and time-consuming. So I'm looking for something simpler to do instead. So here's one step in the right direction. I could perhaps consider something that a method in the machine learning community is called the perceptron learning rule. So this says, well, instead of getting the exact gradient by calculating the full marginal, instead get an approximate gradient that I can calculate from just simply the difference in sufficient statistics between the true setting the parameters and just not a whole distribution over what the model says it should be, but just a single output that the model thinks is highly likely. And so I avoid the need to calculate marginals. I just need to have the model effectively do optimization, find a single good scoring configuration, and I'm set. And this is definitely definitely easier. But again, these models are so complicated that even just finding a high-scoring configuration can be incredibly expensive. It's the kind of thing that I'm going to have to do at test time. I can't avoid it completely. But at learning time, this kind of step is deep inside of an inner loop that's adjusting parameters, and I just don't want to do it so many times. So I want something even simpler. So here is our new method, which we call sample rank. And this works by learning to rank intermediate solutions. So I'm going to do a lot of work in my learning, a lot of beneficial parameter adjustment without waiting until I get all the way to the end of what the model thinks is its most recommended output. And I'll describe how it works as follows. Let me first start by motivating ranking instead of classification. So in essence, in the coreference problem, what I'm talking about here is instead of training my model to look at, say, some partitioning of some mentions and to say, well, this one is a correct partitioning. It's a good coreference decision. I should classify this as a yes, positive example. And here's a bad one that it combines she and Mr. Powell. I should label that as a negative one. I won't do that. Rather, I'll train my model to simply express preferences between pairs of outputs to say, well, this partitioning is better than this partitioning. And why is that a good idea? Well, it's because in general, there are many partitionings that I'm going to visit along the way or that I might even produce as output that will still have errors in them and I just want to be able to know that I'm headed in the right direction, or that I'm expressing the right preferences. So here, George is should not be in this partitioning, but still the partitioning on the left is better than the partitioning on the right that has some gender violation here. Okay, so how do I leverage this ranking principle to do a very fast, good job in learning these things? I start with some configuration. Here these green ovals are representing some kind of coreference decision in my partitioning. I propose some random jump to some new configuration. Here I made some split of the little flat oval here, and I can examine the model score, the unnormalized model score for where I came from and where I went, and look at the difference between them. And so here what this difference tells me is that it's -23. The model does not preferred where I was before over where I ended up. Then I can also look at my labeled truth. Remember, this is not at test time, but at training time. I know what the true partitioning is, and I can look at each one of these hypothesized partitioning and ask myself which one is closer to the truth, and realize that it has the same preference. So that all seems good. Well, this model score says that I'm going to reject this jump. I'm going to go back to number 1, and I'll propose a different jump instead. So here I go, and I'll propose this jump instead. Here, then again, I ask my model for the difference in model scores between these two. Which one of these two does the model prefer? And here the model score is positive. It says, I like where you jumped. I liked it better than where we were. Then I ask the truth. According to the truth, which one is better? It gives a negative number. So actually, according to the truth, where you were before was better. So here it's like a fundamental level. The model is ranking, disagrees with the truth ranking. And this is an opportunity for a parameter update. I essentially do a perceptron-style update on the sufficient statistics of these two options, and adjust my parameters accordingly, and then continue from there. From here, I make another proposal. Here again, the model and the truth agree with each other, but they're both negative. I go back to 3, consider another jump, and go on from there. So, what are some interesting properties of this? It's not exactly perceptron, but it's like perceptron, and we have a new proof of convergence under marginal separability that this also has some of the nice properties that perceptron has. And another thing that I find interesting about this is that this is different from maximum likelihood. And if you think about what maximum likelihood is, it says, maximize the likelihood of the true correct output, but it expresses no preference about what scores you should give to the runner-up outputs that are the incorrect ones. Here we're saying that I want to find the parameters that correctly rank the incorrect solutions. So in a way, this is more constrained than maximum likelihood. And although we haven't, and it's our intuition, as of yet unverified, that these extra constraints may help in regularization, may actually help us produce more robust models. Okay, I'm going to skip over the model. Yes?
It seems like most things which are incorrect are going to in fact be very incorrect and not be very useful at all. And trying to distinguish a rank between them is going to be fairly arbitrary.
Right. Yeah.
Do you comment on that?
Yes, absolutely. So among the space of all possible configurations, yes, the majority of them will just be so far off that it's hard to say anything. During learning, this method is doing inference, stepping in the direction that it thinks, in which the model thinks things are getting better. And so the intent is that it's spending most of its experience and its learning experience in the regions that are getting closer to the truth. Yeah. But this is still wandering further from the truth than, say, contrastive divergence, Jeff Hinton's method that you may or may not know about, which essentially always starts at the truth, makes just a few MCMC jumps away from the truth, and takes gradients from there. This is more like listening to the model from the beginning. Yeah. Anything else? Okay. Okay, so in summary, we're using Metropolis-Hastings for inference. This allows us to freely bake in domain knowledge about fruitful jumps. And Metropolis-Hastings has the machinery necessary to safely take care of those biases. And we're using sample rank. So how does this work? So let's take a look at results on this classic DARPA-provided newswire data set that people have been banging their heads against for years, actually. In 1997, the state-of-the-art results in coreference on this data set were at 65%. After another few years' worth of efforts, it had crept up to 67%. A few more years of effort, the state-of-the-art got up to 68%. And we were able to jump all the way to 97% by using the techniques that I just described. So we were incredibly proud of ourselves. And the benefits come both from using first-order logic as features and using this rank-based training. Okay. I believe that I am short on time to talk about information integration. I'm going to skip through that so I have just enough time to tell you a little bit about REXA. Essentially, information integration is the problem of combining two databases together where those databases have different schema. Like here, first name and last name are separated. Here, they're combined. Different fields may have different names for what's fundamentally really the same field. And doing this successfully involves schema matching, doing coreference, and normalization. And what we essentially did was put all of these steps into one giant graphical model, a graphical model for doing schema matching, which is sort of like coreference of database fields, and coreference of the field values themselves. This is like coreference among the rows of a database, and put them all together into one massive graphical model, following sort of the storyline that I described from the very beginning. Do learning and joint inference in this model according to the methods that I just described on pretty complex data about people from faculty and alumni listings off of computer science department web pages with various different kinds of schema that you can see here. And we got some results that look quite good. So here we see, so just look at this F1 measure for how we measure performance. You can think about this as, it's percentage. 100 is the best you could get and higher is better. You do them in isolation, you do them in a cascade, or you do them jointly, and joint inference is always the best. And sometimes it's really quite dramatic. And schema matching, we go from 50% up to 71%. So we're quite pleased with this. Okay. All right. So let me, I guess I'm running a little bit late, but I have hopefully time to wrap up by explaining a system that we've been building that leverages a lot of these techniques, that really aims to do data mining on ourselves, on our own research community, which I find tremendously motivating, both because I'm intimately familiar with this data and I know it and I understand it, and because the tools that we build are useful to ourselves. We'd like to better understand the structure of our own research areas. The structure can help us, knowing these things can help us learn a new field, can build tools that aid collaboration, can help us map how ideas travel through social networks of its researchers, etc. So it's about 1.6 million research papers that we spidered off of the web. It's a search engine over computer science research papers, much like CiteSeer here on the left, or this system called Cora that I built actually in the mid to late 90s when I was at Carnegie Mellon. And sort of also like Google Scholar, which is the 800-pound gorilla in this arena. But it has sort of a key different worldview, which is that these previous systems see the world like this. They know about research papers and the citation links among them, and we want a much more rich worldview that knows about many more first-class deduplicated cross-referenced objects and the relations among them, so we can say something about all of these objects and how they interrelate. So here's the home page. You can enter a query in this search box. Say you search for table extraction, and you get back a list of hits that look like this. These are automatically extracted titles, authors, venues, years, abstracts. We can click on a paper title and go to a page that looks like this. This is an automatically generated home page for this paper that lists, again, the abstract, the outgoing references, the incoming citations, automatically extracted BibTeX entry. The idea is that I would never type another BibTeX entry again in my life. And unlike Google Scholar and CiteSeer and the rest, people are first-class objects. So I can click on a person's name and arrive at a home page for this person that was generated by the system. This is contact information automatically extracted off of their website, off of their homepage. It was actually an undergraduate research project to use a face finder to automatically find people's faces and crop them and put them up here. Here's a list of publications sorted by time here. We could also sort them by citation count. Here are a list of authors, co-authors, sorted by time. I could also sort those by count. So according to this data, Jamie Callan is the person that Bruce co-authored with the most. I can also look at not the co-authors, but the cited authors. Who does Bruce Croft cite? And it's actually, it's true of just about everybody that you cite yourself the most. It's not in no way unusual. We can see that another person that he cites is Hector Garcia Molina, who is a database researcher at Stanford. Here are citing authors, people who cite Bruce Croft. Here we see Doug Ord, who's an NLP researcher at Maryland. And so in some ways this is giving us some sense of where does Bruce sit in the research community. It's telling us in a way he takes ideas from the database community and passes and processes them, adds to them, and adds them onto the natural language processing community, which is not such a bad description of where Bruce sits in the research community. For other papers, we've extracted information about from the acknowledgement sections about the grants that funded the work. So you can click on this grant entry and go to a homepage for the grant that gives the grant abstract as well as all the other papers that were funded by this grant. So the National Science Foundation is interested in measuring the impact of their grants, and these are providing them tools with ways to do that. We can also search over people instead of papers. Enter a search term and get back hits that are people. So you're looking for an expert in machine learning and reinforcement learning. Here's a list. We've also used these latent variable Bayesian models to process the full text of these articles and discover research topics, about 400 of them. Actually, in the newest version, there are more like 1,000 or 2,000 fine-grained research topics that we've discovered, with keywords that describe what the topic is all about, something about how this topic sits in relation to the other topics in terms of incoming and outgoing citations, as well as its profile over time. So we can see information in interest in information retrieval has been rising. Poor old neural networks, nobody cares about neural networks anymore. And build these graphs of essentially citation volume among them. So I have more to say, but I think I'm already desperately late. I'll bring it to a close here, and perhaps there's time for some questions. Thank you very much.